Krebs cycle, it throws off the coenzyme A, it becomes in a CO group, and then that will combine, that will become citrate, and then the isocitrate, and then from here to alpha ketoglutarate, we give off CO2. Between this step here, alpha ketoglutarate, succinyl coenzyme A, we give off two products. Succinyl coenzyme A to succinate, we make a molecule ATP. From succinate to fumarate, we give off high energy electrons, not as high to be accepted here, but instead of wasting it, we want to be picked up by another electron carrier and then ultimately another molecule. So basically what we're doing here, just like glycolysis, we're going through a lot of steps. And we basically we need to be off our phones. We basically are hydrolyzing the molecule to where we can harvest as much energy as we can out of that molecule. So that's why it requires so many steps. And also, if we were able to take a molecule of glucose and we literally blasted it open to capture some of that energy in the form of ATP, the heat that's given off by that molecule of glucose would be so hot it literally would nuke the cell. So if we want to harvest the energy, that's why we're having all these different steps, so that we can gradually release the energy in a controlled way and then be able to have an electron carrier pick it up. Then we're going to see is going to take it to the electron transport chain or have an actual molecule of ATP produced. That way we don't waste it. But we see 30 to 40% of the energy stored in a molecule of glucose is still going to be, 30 to 40% is going to be converted into ATP. The other 60% is going to be given off as heat. So we still have a large amount of heat given off in the production of ATP. That's why when you exercise, and you're exercising your muscles, that's why you get hot. Because your cells are your muscle cells are rapidly going through this process here. And it's producing a lot of heat because it's breaking down a whole bunch of glucose molecules for ATP production. Okay, so we're okay here? All right, so let's do the products. Remember, it's going to go around twice because we have two pyruvates. The two pyruvates got converted into two acetyl coenzyme A's. And do not forget what was in the preparatory step. Figure them out. So what do you have here?
6 CO2.
Okay, so we have 6 CO2, okay?
2 FADH.
2 FADH. Okay, why don't you stop? And thank you very much. And that, because I know some people are just dying to count. 2 what? Okay, so let's stop and count the NADHs. Okay? So we've got one produced right here, right? 1, 2, and another one in the preparatory step. So 3, and remember we have to go around twice. 6. Good. So we have 6 NADHs. Okay? What else do we have produced? The ATP, how many? 2, good. Okay, is that it? So we have 2 ATP, 6 NADHs, 2 FADHs, and 6 CO2. Yes? Yes? Yes. Okay?
Yes.
So, all right. Okay, so then now those high energy electrons, which are in FADH2 and NADH, is going to now be transported right next door to the mitochondria. So let's just put our mitochondria back up here again. So our mitochondria. So here's our mitochondria right here. Outer membrane. And so we have an inner membrane. This is the outer compartment. Thank you. The matrix. or sometimes called the inner compartment. Okay, this is where the Krebs cycle took place, in here, in the matrix. Now the ETS is going to be located here on the inner membrane. So it's just right next door. So here's where you do have a lot of oxidation reduction transferring of the electrons and molecules accepting the electrons. Okay, so next topic is going to be the electron transport system or chain. So let's do that one.
There's also the inner, the matrix to the inner.
No, we were just drawing that. We're just doing the anatomy of the mitochondria. We haven't done it yet. That's what we're going to do. Okay, the electron transport system or chain. So it's abbreviated ETS, ETC. So something along that line. Okay. All right. So we're located on the inner mitochondrial membrane. So there's a number of protein molecules, and they're organized into 4 protein complexes, which makes up this chain. That's this. Help me out here. Is that an E or U? E? Plexus? Is that look right? It's a U. Okay. Plexus. Oh, plexus. There we go. Okay, so a lot of coenzymes like coenzyme Q, number of cytochrome. These are examples of the protein molecules that are there. They make it so they're organized. So these are protein complexes. They're organized in a staircase fashion. Yes. You don't have to know the protein complexes or the line or the number of the steps or anything. But I oftentimes tell students the analogy of this. So here you basically have a staircase. And so let's say you have a billionaire. Okay? A billionaire, right? No. Yeah. Well, whatever. Doesn't matter. Anyway, so you have a billionaire, and he's being very, very generous, or she's being very generous and says, I'm going to give all my money away. And so I'm able to go down the staircase and let's say exchange for eternal life or whatever. Okay. But anyway, by the time he or she gets down to here, she has to be a pauper. What's a pauper? You've heard of pauper, right? It's a literature. Okay, what's a pauper? That one in England, 1800s. I forgot the name of it. But you guys need to get out more often. Someone who's poor. Okay. Well, anyway, the idea is that you have this guy or woman, lots of money, travels down the ETS. By the time it comes down here, he or she has no money. Has to give the money away. Okay. So there's the dollar signs. And we're going to see these dollar signs are going to be the electrons and not the electrons, the energy that he or she's going to give away. And we're going to see that's going to be used to make ATP. Okay, the electrons are going to travel along this chain here. That's why it's called an electron chain. Okay, so you get the idea? Kind of the concept? Yep. Yes? Okay. So we have those electron carriers. So what are the electron carriers? You have your NADH and your FADH2. Okay, this one is higher in energy, your NADH. So the hydrogen is removed off of the NADH, freeing the electrons, also the energy. So NADH is able to enter at the top. And so once the hydrogen is removed, the hydrogen, we're going to see what happens to the hydrogen. And then the electrons are going to basically go from one molecule to the other. Reduce, oxidize, all the way down to here. The energy is also going to be given off that was stored in these electrons. In order for the electron to go from one molecule to another, it has to be at lower energy levels. The FAD doesn't have as much energy, so it enters a little bit lower, in the chain. Somebody's in there. Okay, so the ETS, the electron transport system or chain, basically is located in the inner mitochondrial membrane. That's what we have in the little black dots there. It consists of protein complexes that basically is able to accept and give away, reduce, oxidize electrons. And so basically, accept electrons, give them away. The coenzyme Q cytochromes make up the bulk of the molecules themselves. So here are our high energy molecules. Hydrogen ion is removed, and so freeing the electrons with their energy. The electrons will travel down. They'll be given off, accepted, given off, accepted, given off, accepted, all the way down to here. Remember, they have to be a pauper down here. They have to have no energy at that point. So that energy, as they're traveling down this chain, is going to be given off, and we'll see it'll be used to pump these hydrogen ions across this membrane to the outside. Okay? And so that we're going to form a pH gradient, and we're going to form an energy gradient. Okay, but let's look at the electrons right here first. The electrons are down at the end of the chain. They have no energy, so oxygen is going to come along. It's going to grab those poor electrons because they're poor. Nobody wants them, and we're going to form water. So O2 is the final electron acceptor. And this is the reason why we breathe, for this part right here. Do you think I might ask you that on the test? Absolutely. That important. This is why you breathe. You breathe because oxygen is the final electron acceptor at the end of the ETS. Without it, we only have like 2 or 3 minutes worth of ATP in the body. So let me tell you how a poison works. For instance, cyanide gas. Cyanide gas is one of those that blocks this pathway. And what it does is that it prevents these, if you have no oxygen right here, even though you may have them going down the chain, it starts slowing the chain down because you have no oxygen taking these electrons. So these electrons accumulate right here. You have no electrons, or you have no oxygen because you're breathing in cyanide gas instead to get all these electrons here, so the chain stops. So therefore, if the chain stops, you're not going to be giving energy or hydrogen ions eventually through chemiosmosis, which is the production of ATP elsewhere. You're going to not have ATP because you don't have oxygen right here, and you'll die in a couple minutes. Okay? So many of the poisons work that way. As you know, many of the poisons will block the sodium channels, or they'll keep them open or something along the line. But some poisons work in this way, where they block the ETC thing, or they prevent this happening right here at this point. So can't stop it, obviously. So, okay? All right, so that's why it's important. That's why we require oxygen. That's why we are breathing in oxygen for this part right here. Okay, any questions? So now the energy that's been given off here is going to be used to pump hydrogen ions into the outer compartment. So now we're going to basically accumulate a lot of hydrogen ions here. We're going to store some energy too, because not all the energy was required to pump it. But so you're going to get a pH gradient. And you're going to get an energy gradient. And as you know, once you have a gradient, you want to, what? If you have a gradient, what do you want to do with that gradient?
low.
Yeah, you can go from high to low, you wanna get rid of the gradient. So here you have lots of hydrogen ions here, lots of, more energy here than you did in the matrix. So now those hydrogen ions will wanna go back across to back in, because they were pumped out. They were pumped out from here, so now they're out here. But the membrane is not permeable to the hydrogen. So therefore, they have to, in order for them to cross back, they have to cross through a molecule called ATP synthase. Okay, enzyme associated with it. And so you have a lot of these ATP synthase which are intermingled on the inner membrane. And so as the hydrogens go by, they spin this ATP, or excuse me, the ATP synthase molecule. And so in one of the handles I have a picture of it. And so they spin it as the hydrogens whoosh by, and they will then cause the phosphate group to be attached to ADP to form ATP. This is chemiosmosis. Pumping of hydrogen ions, osmosis. Pumping of hydrogen ions across the membrane to one side, allowing them to passively, creating a gradient, allowing them to passively cross. And so when they cross, they have to pass through these ATP synthase molecules. And when they do that, this molecule spinning is able to combine these two to form ATP. This is the process of chemiosmosis. We make the bulk of the majority of our ATP this way. And I mentioned yesterday that Peter Mitchell won a Nobel Prize for this in the 1990s, I think. Okay? Yes? Want to do it again?
Yep.
Yeah. Okay. All right. So ETS right next to the Krebs cycle. So basically consists of these molecules here, groups of proteins. Their function is to accept and give away electrons. And so each time that they accept and give away electrons, it requires less and less energy to do so. So the energy that was stored on those electrons from glycolysis and the Krebs cycle is going to be given off. The hydrogen is also given off, and so these two is used to pump the hydrogen ions outside of the matrix into the outer compartment. Okay, so eventually at the end of the ETS, we have electrons which are low in energy, and they're picked up along with oxygen along with hydrogen to form water. So oxygen serves as a final electron acceptor at the end of the ETC. Okay, on the so you're pumping out all the hydrogen ions out here. You form a pH and energy gradient. The hydrogen ions want to go back across. The membrane is not permeable to the hydrogen ions, but they can cross via these transporters here, the ATP synthase transporters, but they're a specialized type of transporter that when the hydrogen goes by, it spins this molecule, and that would then in turn be able to put these two together to form a molecule ATP. Okay, this is the chemiosmotic theory of ATP production. So we saw ATP made two ways: substrate phosphorylation, oxidative phosphorylation, and this is oxidative phosphorylation. Got that? Okay. Okay, so now let's see how much ATP that we have made for a molecule of glucose. So, one molecule of glucose. So we need to see how much ATP that we made. Okay, so how many ATPs were made outright through substrate phosphorylation? So look in your notes. Go back to glycolysis. Go back to the Krebs cycle. So some were actually made outright through substrate phosphorylation. So look at glycolysis. What was the net yield of glycolysis? 2. Okay, so we have 2 there from glycolysis. How many in the Krebs cycle? 2. Okay, so we have 4 that are made outright. You see where that came from? Okay. Okay, how many FADH2s did we make from molecule glucose?
2.
each one can yield 2 ATPs, they have enough energy to do that. So how many ATPs? 4. Okay? I guess we should kind of put our screen over here. 4 ATPs here from this one, okay? And then 4 from this one, okay? And the NADH can yield 3 ATPs. So those electrons can yield enough energy to produce 3 ATPs. So how many do we have?
10.
It's like 8 right here.
We have 8. How many in the glycolysis? 2. How many in the Krebs cycle? 6. We have 8. Oops, should put 8 here, sorry. 8. So how many do we have? 24. So how many do we have altogether? 32 ATPs. Sometimes you see these in, depending upon the cell, it might be 2.5, it might be 3.5, depending upon the cell. So not all cells are like this, so you can get 32 to 36 ATPs. That's how many you can actually produce per molecule glucose. So if we said we have 2 and 3, but sometimes it can be 2.5, 3.5, depending on some cells or 30 cells or whatever. But just as long as you're in this category here, the 30s, you're okay. This is under aerobic conditions. What about anaerobic conditions? It's low in O2. So, do organisms go through glycolysis? Every single organism goes through glycolysis. And you see it produces 2 ATPs. Organisms go through the Krebs cycle only if there's oxygen. So would the organisms go through the Krebs cycle if there's not enough oxygen? No. So they wouldn't go through chemiosmosis either, right? So therefore, they would only be able to use the 2 ATP glycolysis. So we see here, under low O2, we only produce 2 ATPs per molecule of glucose. Under aerobic conditions, we produce a lot more, up to 36. So 18 times more. Okay, very efficient. So, as we said, about 30 to 40% of the energy in the glucose is produced as ATP, and the other 60% or so is given off as heat. Now, this heat is then used to maintain our body temperature. Remember? So, because we are endotherms. So that's what we mean when we talk about using metabolic heat to maintain our body temperature. This is part of one of the pathways we use the heat. Any questions? So how are we doing? Let's see. The mixture for the products here, so you know for the products here, ATP and water for the ETS.